So, emergent features of self-organizing systems, in other words, swarming for cyber applications. This is a talk that is going to be focusing not on specific techniques that we have available right now, but more of a vision into the future. I am Dr. Sven Brueckner. I have my PhD in computer science, artificial intelligence, and have been doing 15 years plus R&D and swarm intelligence theory and applications. Cyber is one of those that we're moving into. Our company, Axon Goes Sentinel, part of the Mark 37 accelerator in the spring. Mark 37 being a sponsor here of this conference. We are looking to build cybersecurity products for mobile devices and the Internet of Things, and that is going to be part of my presentation today. If you want to take an early peek at what we are doing, our first Android app is out as a free public beta. Konica, look it up if you like. Part of Axon AI, which is looking at more than just cyber as applications for swarm intelligence for self-organizing systems. So I'm going to be talking a bit about what swarm intelligence research is looking at and how that can be applied to mobile applications and the Internet of Things. I'm going to sketch an approach that we are following right now. So as I said, self-organizing systems with emergent system-level features, in other words, swarming systems are all around us. Nature has demonstrated in many applications on how to take very simple entities and combine them adaptively, robustly, scalably to create complex system-level behavior. You've just got some photos there. We've got, of course, our classical ant systems and the bees swarming. We've got the fish schooling to create the appearance of a much larger animal to protect themselves from predators. We have swarming going on, self-organization going on, of course, at the bacterial level too. But then at the other hand, even humans in groups do it, crowd behavior, market behavior. Those are all examples of swarming systems, of self-organizing systems where at the aggregate, new behaviors, new patterns are emerging that are not encoded in the individual level behavior. So with all these examples around, the question is, why are we still programming our applications, our solutions in the traditional top-down centralized fashion? Why are we trying to spend an enormous amount of time on knowledge engineering, on explicitly enumerating all potential conditions our system has to face when we can create complex behavior by combining many lightweight individuals that are autonomously acting in a shared environment that do not communicate directly with each other, but through the manipulation of the environment, the principle of French biology goes say called stigmergy, that can deal with noisy information and a heterogeneous, constantly changing population. And out of all that, create a system at the system level where the functionality emerges robustly, adaptively, at a large scale, and has capabilities of learning also built in. So when we look at engineered systems, especially in the Internet of Things, we are seeing an architecture that is resembling all those natural systems that we're dealing with. So some of the statistics that are being thrown around, whether they are true or not, the projections are that by 2025, there will be more than 70 billion internet-connected devices. Those are simple devices that do their things, whatever they're doing autonomously. And more than 1 trillion connected sensors. So if you're trying to build applications, whether it's for securing your Internet of Things, or whether it is to provide those various functions that you are hoping to get out of the Internet of Things, really you've got to look at engineering those devices into an aggregate, into a coherent system by using self-organization and emergent as design principles. I said I work on swarm intelligence, really swarm intelligence as a special case of artificial intelligence in the computer science world takes its inspiration from those natural agent systems. And then you have two paths within the community. You have from these observations and analyses of naturally occurring self-organizations, you have people who are focusing on building models of what happens in nature. How can we explain that natural systems create these functionalities? How do ants form their paths, or the termites create their air conditioning systems in their mounds, and so on and so forth. So models of the real world that are compared against the natural system observations. But then the second part is more from the engineering perspective. Okay, if you understand and have models on how nature creates self-organizing systems, can we derive the basic principles that that design really takes? As I was showing on an earlier slide, things like keep your agents small, do not have direct interaction, and so on and so forth, the laundry list of design principles, and apply them as an engineering methodology to create new systems. So that's really where my work has been focused on, looking at swarming robotics, looking at planning and predicting complex behavior, looking at coordination of resources of various types, and then finally looking at cyber applications where you are tying together many different devices, be it a sensor network or be it a robot or a network of applications. So how would we want to do that if we have a collection of physical devices in an infrastructure where the individual devices are limited in their capabilities in terms of bandwidth, in terms of their computational power? A Nest thermostat does run Linux. It is a little computer, but overall it's not going to be the power of today's smartphones. It's going to be more simple. Where we have devices coming and going all the time, so where we have this high churn that we have to deal with. Well, we're taking the perspective that what we call a device in our infrastructure is really the combination of a physical unit with an autonomous agent, so a piece of software representing that unit to take any kind of control actions on that unit, or take information from that physical unit, so kind of our interface, plus provide that device with the ability to host other little software agents that could come and go through just a standard message passing protocol. If you have that kind of infrastructure, we can then use those agents to create a self-organizing peer-to-peer overlay and create virtual topologies where, rather than just sticking with the primary communications channels that are available from one device to another, route messages across the network of devices according to certain objectives. So I want to have devices of similar characteristics be tied close together in a peer-to-peer overlay. Well, you can achieve something like that in a self-organizing fashion, where devices basically search for other devices to connect to. So as an example, in that peer-to-peer overlay, we can then run other agents that are kind of spreading out information, that are taking local information and transforming it for the use of neighbors and neighbors of neighbors and so on. In that fashion, we can then create applications as emergent features of that process of these swarming agents, just like you see in these natural agent systems, like these insect colonies or other swarms that we find in nature. So one example of that, One example of that is our first application that we are working on right now. Say for instance we have our mobile devices where we're taking local observations like, okay, what's the current CPU load of the device, or the memory consumption, or ratio of inbound, outbound traffic, or other indicators of device behavior. Use the self-organizing peer-to-peer overlay as one method to create a topology where devices with similar characteristics find themselves connected to other devices that have the same or similar characteristics. so that you can traverse that topology, and as you're discovering devices that are suddenly stand out like a sore thumb relative to all their neighbors, find those, identify those as suddenly changed, as potentially abnormal behavior, and start highlighting those. So you can do all that with local choices, with agents swarming in this topology that is created on the fly by the network of devices. And out of that, you can get situational awareness. You can know what type of devices are in your system right now, what are connected. You can know what the characteristics of those devices are, as well as detection of abnormal behavior, potentially threatening behavior, by looking at these abnormal or deviations from the learned normal in your network. So that's the starting point for our development that we're doing at Axon Ghost Sentinel, and expanding from there, adding more capabilities, more features, always with these principles of engineering self-organizing systems in mind. All your choices are local, all your behaviors and rules are lightweight, so that you can scale up to a large number of devices in your network, as well as deal with very weak devices, if you want to call it that. And with that, the short introduction is over. Oops. So, any questions, comments?
Out of curiosity, are there efficiencies gained in terms of resources in the swarms versus a dedicated hierarchy?
Well, the advantage of using swarming rather than self-organizing systems rather than explicitly coded hierarchies is, for one, to deal with the dynamic situation where creating a hierarchy, if you try to do a top-down, creates scaling challenges as well as just reactive challenges. Also, the advantage of doing the swarming in the network and doing basically all your calculation, all your operations in the network is that it's pushing the computation to the edge, and thereby you're saving the bandwidth of not having to pump out all status information into the cloud or whatever, and do analytics there. So that's really the purpose of the swarming architecture, to push the calculation and operations into the cloud, into the network, to the edge.
I do networking, so I mean that's my primary job, so that's why I'm curious. This has an assumption of a network in place, so it's less for self-organizing a network at this stage.
You mean self-organizing the physical connections?
Correct.
Right. I mean,
and the linkages between the nodes.
You can create that out of the swarming too. I mean, you can start with one set of linkages and then have the swarming operating over that set, basically identify, okay, which linkages should be adjusted and recreated so that you get more optimal traffic. Or
that's where I was curious about what the overhead, like, I know that I've got packet overhead, protocol overheads. I'm wondering for a swarm-based protocol what the overhead would be. It's theory. I mean, we don't have a working, it's a widely adopted model, to be a better way to say that. So that's where I am most interested in seeing where this type of research goes, above and beyond, what we can do with it. The robotics models or something like that are pretty fun.
Do you have any suggested open source libraries or reading regarding swarming in the event we want to implement something without using it?
Well, there are some packages out there, most predominantly used or widely used as Repast, which is a successor to Swarm, which is an architecture that originally came out of Santa Fe. I believe Repast is maintained by University of Chicago. Java-based framework with lots of example models. If you just Google swarm intelligence as keywords, self-organization, emergence, you'll find plenty of reading. There's a long-standing series of conferences called SASO, Self-Adaptive Self-Organizing Systems, that happens each year, alternating between Europe and the United States, that has good publications, entry level. If you are interested, they typically have tutorial sessions in the first days. It's always a good place to start.
Does this not lend itself to like biological calculations, like Mendel's law and things like that as well? Since you're talking, is originally with biologics? Like
Well, it's
DNA?
not like it's not like genetic
No.
computing or anything
Nothing.
like that. No, it's really software engineering, but bottom up rather than top down. So it's a different methodology for software engineering. So at least that's the way I see it. Even when you have it in robotics, robotic platforms, it's still the software that controls the robots and how to coordinate and all that. Yeah.
What's the kind of scale that you're looking at? Like, you mentioned that there's a beta of a smartphone app.
Mm-hmm.
Is that going along the lines of where like my smartphone would be one of the nodes in the swarm, and then everyone else is?
That is the vision.
Using
I
it.
mean, the current version of that is that the swarm is actually not physically running on your app. In your app connects to the server where the swarm lives. So right now the agents are still sitting in a central server doing their swarming thing in that box. But our next versions that we're working on is going to more and more push the boundaries where at the end of the day the real vision is that there is not going to be a central server anymore. There is your device and my device and everybody else's device talking to each other, supporting that swarming architecture so that we are creating the intelligence in the network amongst us. Okay. Right back there?
What are the vulnerabilities you think that this might introduce that would not apply to the traditional approach? Because when I think of swarms, I think of lemons going off the cliff.
Yes.
Or whales teaching themselves for no apparent reason.
Traditional software is brittle to even subtle changes. If you hack into the software, if you find a way in, just like you talked before, if you know the hacking tricks to get into the software, you can control the whole thing because the control is in the software. If you hack your way in, you have control. Self-organizing systems, the individual piece of software, even if you hack your way into the code, is not going to give you control of the system. If you try to get ants out of your kitchen, they have invaded your kitchen, they've built their paths, killing the individual ant is not going to do anything good. You will have to basically wipe out most of the population and preferably also the chemical markers, the pheromones that they laid down so that they're guiding in new ants out from the colony. So from a vulnerability perspective, self-organizing systems are or can be more secure because the software itself is not going to tell you what the system is doing. That's a self-organizing emergent feature of all the interactions. Taking control of an individual agent, like, okay, I'm going to install the app and then I'm going to hack it and I'm going to send different signals. That's just one among thousands and thousands of participants in the swarm. That's not going to be changing the lemmings, changing the overall behavior. But if you understand, if you're basically knowledgeable enough that you understand what the system level behavior is, you can start faking it out, sending enough fake signals to affect many of the participants. At some point, you will be able to take control and send all the lemmings off the cliff. But it takes a lot of effort to do that. Any other questions? Well then, thank you for your attention.